Hello, chemistry students. So today we're going to talk about entropy and Gibbs free energy. So what is a spontaneous reaction? A spontaneous process is one that proceeds on its own without any outside assistance. It just happens. This spontaneous process occurs in one direction only. The reverse of any spontaneous process is always non-spontaneous, meaning it has to be helped along by applying an external source of energy. So we have a gas and it's all on one side of this container. And if we open the valve there, we would not expect the gas to stay on that one side of the container. Kind of like when we have acetic acid in a container inside the lab, eventually, rather quickly, the whole room is going to smell like acetic acid. And that would be a spontaneous diffusion or a spontaneous process. It would be non-spontaneous in order to get all of that gas back into one side of the container or one side of the room. So let's look at this first example here. Would we expect the following processes to be spontaneous or non-spontaneous at the stated conditions? So these are things that you already know and that you can figure this out. So we have some liquid water and it goes to solid water. In other words, we've got some liquid water that we can drink and it's going to turn into ice. The temperature is negative 10 degrees C in 1 atmosphere. 1 atmosphere is room pressure, what we feel all the time, but negative 10 degrees C is not. At room temperature, we would not expect this process to just happen spontaneously. But if we were in a room of negative 10 degrees C, since water freezes at 0 degrees C, we would expect this to happen spontaneously, this process right here. So this would be spontaneous. And I'm just going to put spont. Next example. So we have some liquid water and it is going to a gas, hydrogen gas and oxygen gas. 25 degrees C is just slightly warmer than room temperature. In our room at school, it's about 25 or 23 degrees C because we have AC on. So this is just slightly warmer, not much warmer. And if I put a glass of water out on the table, we would not expect it to spontaneously turn into hydrogen and oxygen gas. Thank goodness, because we would have some explosions, I'm sure. So this second reaction is non-spontaneous at this temperature and pressure. Third example, so we have some table salt, NaCl, it's a solid. And we're saying that it's going to turn into sodium ions aqueous and chloride ions aqueous. And we poured a gram of sodium chloride in a liter of water at room temperature and room pressure. We would expect it to dissolve. So this process is spontaneous. Instead of the word spontaneous, AP prefers the term thermodynamically favorable. So you will hear me say that quite a bit. And we'll be using that term from here on out, along with spontaneous. So just because a process or a reaction is thermodynamically favored, it does not necessarily mean that it will occur at an observable rate. In other words, that we can see it in a matter of minutes or hours. Like we can see salt dissolve in a matter of minutes. We can see water freeze in a matter of hours. But we can't see iron and oxygen reacting to form rust in a matter of minutes or hours. This usually takes days, sometimes weeks at room temperature and pressure, but it is spontaneous. It says we're going to discuss things to speed up a reaction next unit. We've already done that in kinetic. Let's talk about the next thing. What makes some processes spontaneous and others not? It's dependent on 4 major factors. The first one's enthalpy, which is delta H. You guys have already learned about that. Temperature, if you notice here, it doesn't say a change in temperature, just temperature. And entropy, which we're going to talk about here in just a minute. That is delta S. These 3 factors right here affect whether or not a reaction will be spontaneous, and that is delta G. So delta G is Gibbs free energy, and it uses enthalpy, entropy, and temperature to determine if a reaction or a process will be spontaneous. Entropy is the amount of disorder of a system We also call this freedom of motion, randomness of arrangement, and energy distribution. The more freedom of motion a system has, or a group of molecules has, the higher the entropy the system is. You're going to hear me talk about microstates. So I'm going to write this down here, what a microstate is. Microstates describe the probability a group of particles might occupy a particular set of positions in space at any given time. This set of positions is equal to the microstates. So the more microstates a system has, or a group of particles has, the higher the entropy. So let's use an example. Right here we have a solid. It's highly ordered. It has a low entropy. But once we add some heat to it and it turns into a gas, it has high disorder and high entropy. Now let's talk about the microstates and the solid. This molecule, this atom right here, can occupy this position and next to these three molecules right here. But it cannot spontaneously go over here because it doesn't have that freedom of movement that a gas does. So it can only occupy about these three positions and vibrate at a very quick speed. But once we add energy to it, the IMFs here will break, and this molecule right here at any given time could be located right here, could be located right here, could be located right here. So it has many other different probabilities of being in a different microstate. Could be over here, could be over here. So a gas state has many, many more microstates, probabilities of being in many, many more microstates than a solid does. Therefore, it has more freedom, a gas does, has more freedom of motion, more randomness of arrangement, a higher energy distribution, and therefore it has a higher entropy. You will also hear me call energy distribution a thermal disorder. So the higher the temperature that you add, the more heat energy you add, the more the molecules will be moving around. Therefore, it will have a higher thermal disorder. Your randomness of arrangement and freedom of motion. This is describes a positional disorder. A positive delta S or a positive entropy means that a system has more freedom or disorder. A negative delta S or a negative entropy means that the system had went to less freedom or disorder. So going from a solid to a gas, you're going to increase the entropy, so it would have a positive delta S. Going from a gas to a solid, you're decreasing the disorder, so it will be a negative delta S. Entropy increases, or we'll have a positive delta S here, when matter or energy becomes more dispersed. So there are several examples here that we're going to go over with that. So if a volume of gas increases at constant temperature, so we have this box with a certain volume, and it has 5 gas molecules. Okay, those are circles. And we're going to increase the volume, and the temperature is going to remain the same, so the kinetic energy is the same. All right, and here are our same 5 molecules. They're not moving any faster. They're at constant temperature, but they have more space between them. Because they have more space between them, they have more possible microstates or more randomness. So the entropy will increase because the space between them is bigger. This is a positional disorder. When the number of molecules increases in a reaction, let's go down to this example right here. So if the number of molecules increase in a reaction, we're going to increase the disorder, or the delta S will be positive. So here we have 1, 2, 3, 4, 5 molecules, and it reacts in the forward direction, and it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 molecules. So the number of molecules increases. Therefore, the number of positions that any one molecule can occupy in relation to another molecule increases. Therefore, the positional disorder will increase, and the delta S will increase. Another way you can look at this is through a reaction. So over here you have 1 mole of N2O4 and you are making 2 moles of NO2. So the number of moles are increasing, therefore the delta S will increase. A solid dissolves in a solvent to form a solution. An example of this would be your NaCl in a solid form, and it goes to Na plus in aqueous form and Cl minus in aqueous form. All right, this is one way. There are 2 different disorders in this example. We have sodium chloride solid, so we have 1 molecule here, and it is dissolving to make 2 molecules. You could also use sugar, because sugar doesn't break up into ions. You could have solid sugar over here and aqueous sugar over here. In that case, or in either case, it's going from a solid, which is more orderly, to an aqueous where it can move around as a liquid. Therefore, you're increasing the positional disorder. A process where products are in a more disordered state, like solid, liquid, gas. We talked about that on the prior page. Over here is a good example. So we have a crystalline solid. This molecule right here has a limited number of microstates compared to a liquid because it can't move or change positions in here very readily. As opposed to a liquid, once those IMFs are weakened, this liquid molecule within a given amount of time, a short given amount of time, it can flow over here to this side or this side right here. So that one liquid molecule has a probability of occupying all of these microstates. Now, once you've added gas, you've increased the amount of volume that substance can go into. So over here, this one molecule down here can only occupy this volume down at the bottom of the flask. This molecule down here could be anywhere inside of this flask. So you've increased the positional disorder going from a liquid to a gas. So this way, all of your delta S's are going to be a positive delta S. And lastly, when temperature increases, even when you don't have a phase change. So basically, if you're just heating up a gas right here, let's say it's water, and it is at 101 Celsius, and we heat it up to 200 Celsius. These molecules are going to move much faster, so the probability of, in a given amount of time, the probability of one molecule occupying a greater number of microstates is much greater because it can get to all of those microstates much faster. So the entropy would increase even if we're not changing the states. All we're doing is increasing temperature. If you look at this graph right here, we've got entropy on the y-axis and temperature on the x-axis. So if you see, as far as the change in entropy is concerned compared to the change in temperature, entropy changes more with phase changes than it does during a temperature change, just within a temperature change of a single phase. For instance, if we're heating up a solid here, the entropy doesn't change much for every 1 degree Kelvin as it does with a phase change going from a solid to a liquid. The entropy change is much greater with a smaller amount of temperature change. All right, let's talk about this next example. Okay, so for each of the following, decide which substance would represent the higher amount of entropy. 2 separate 1 liter containers of nitrogen and oxygen. So basically we have a 1 liter container of just nitrogen and a 1 liter container of just oxygen, or a 2 liter container with nitrogen and oxygen mixed. Well, the nitrogen and oxygen mixed would have the higher entropy, and the reason why is because there is more degrees of freedom in a mixed substance. Each nitrogen molecule can react with itself or with any other nitrogen molecule, and it can also react with an oxygen molecule. And also in a 2 liter container that's mixed, an oxygen can react with an oxygen, microstate, and an oxygen can also react with another nitrogen microstate, as opposed to in two separate containers where a nitrogen can only react with a nitrogen. Liquid SF6 or gaseous SF6. We've already talked about a gas has more degrees of freedom because it can move around more, so there are more microstates, so it would have a higher entropy. Oxygen gas at a high pressure or oxygen gas at a low pressure. The low pressure would have the higher entropy, just like we talked about right up here with the volume of gas increases at constant temperature. If you have a larger volume, you're going to have lower pressure, and it increases your positional disorder because there's more space between the molecules. Same thing with a lower pressure. Gas A or gas B shown in the graph to the right. So let's look at this. So gas A has a lower molecular speed average than gas B. So gas B has a higher average molecular speed, therefore it has higher average kinetic energy, and therefore it has higher average temperature. So gas B would have a higher entropy. For each of the following, predict if the process represents an increase or a decrease in entropy, and predict the sign of delta S. The first thing we're going to do is look at states. After that, we'll look at the number of molecules. So here we're going from a solid to aqueous, and because of that, we're increasing our entropy, our delta S, because it's going to a more disordered arrangement from a solid to a liquid. You could also look at this and think this is going from 1 molecule to 1 plus 3 molecules, so from 1 mole to 4 moles. That also increases the entropy. Now let's do B. Let's look at the states first. So we're going from an aqueous solution to a solid. We're decreasing the disorder or decreasing the entropy, so it would have a negative delta S. You could also look at it as number of moles. We're going from 2 moles of a substance to 1 mole of a substance. Both of those scenarios will decrease in entropy or decreasing disorder. All right, C. Let's look at the states first. We have a gaseous substance and a gaseous substance and going to a gaseous substance. So they're all gases, so it's not increasing or decreasing entropy as far as the states are concerned. So let's look at the number of moles. We have 3 moles of reactants and we have 2 moles of products. We're going from 3 to 2 moles. We are decreasing the number of molecules, therefore decreasing the entropy. Let's look at D. We're going to look at the states first. We're going from a liquid to a gas. So we're going to more degrees of freedom or more motion or more movement, so we are going to increase the entropy, or the entropy will increase. Over here we have iodine vapor, which is a gas, and it deposits onto a cold surface to form crystals. So it's going from a gas to a solid. We're decreasing the amount of movement that can happen, so we're decreasing the entropy. Solid sugar is added to water to form a solution. So this is going from a solid to aqueous. That's increasing the disorder. If the order is increasing, the sign for your delta S will be positive. Now we're going to do some calculations with entropy. Entropy values are typically reported in joules per mole Kelvin at standard ambient temperatures and pressures, which again is 25 degrees C or 298 Kelvin. Now let's compare some methane, some CH4 to C2H6 to C3H8, which is located right here. Let's compare these 3. What do we notice about the entropy and how it changes as the size of the molecule increases? So the size is going to increase as we go down this way. Size increases. And we also notice that the entropy increases each time. So as molecule size increases, the molecule complexity increases. Therefore, the entropy will increase. Recall the third law of thermodynamics. It states that the entropy of a perfect crystal at 0 Kelvin is 0. Notice that none of the entropy values in this table is 0. And that's because all of these substances are at 25 degrees C or 298. They're not at 0 Kelvin. So the formula for the entropy of a system is delta S is equal to the sum of all the entropy of the products minus the sum of all the entropy of the reactants. This looks very familiar as far as delta H is concerned. The delta H of your products minus the delta H of your reactants. Second law of thermodynamics states that in any spontaneous process, there is always an increase in the entropy of the universe. If the delta S of universe is increasing, then the reaction is thermodynamically favorable. But the formula up above, right here, only calculates entropy of the system, not of the universe. So we cannot use the formula above, just this formula, to determine if a reaction is thermodynamically favorable. We have to use more. So let's do an example. Use the reaction below to answer the following questions. We have 2 hydrogens in a gaseous state plus 1 oxygen in a gaseous state yields 2 waters in a gaseous state. Use the values of delta S in the table above to calculate the entropy change for the reaction. So we know that the delta S of a reaction is going to equal the sum of our delta S of our products minus the sum of the delta S of our reactants. So the delta S of my reaction will equal. Now I'm going to look, my products are 2 waters, 2 moles of water. So I'm going to come up here and I'm going to look for water in the gaseous state because it says it's gaseous. So I'm going to choose this one. Water is 188.84. And I have 2 moles of it, so 2 moles of water, gas. The gaseous water is 188 kilojoules per mole Kelvin, minus all of my reactants. I have 2 moles of H2 in the gaseous form. Let's look what the hydrogen in gaseous form is, and that is 130.7 joules per mole Kelvin. This over here should be joules, not kilojoules. Plus, we have 1 mole of oxygen, gas. And the entropy of that is 1 mole of O2 is 205.1. Joules per mole Kelvin. My moles are going to cancel in each of these. And the delta S of my reaction negative 88.82 joules per mole reaction. Does this sign for the entropy for the reaction make sense? So we need to think about this. It's a negative number, which means our entropy decreased. So let's go back up here and look. They're all in gaseous form, so that doesn't have anything to do with it. We have 3 moles going to 2 moles. So we're decreasing in the entropy here. So yes, we're going in a less disordered state. Negative delta S implies less disorder. The reaction shows a decrease in the number of moles. Therefore, disorder is decreasing. So we've spoke about enthalpy, we've spoken about entropy, and now we're going to calculate with Gibbs free energy. So remember, the driving force for a spontaneous process is an increase in entropy of the universe, but we can't measure that entropy of the universe, the whole thing, unless we have a lot of information. So instead, we are going to look at the balance of entropy and enthalpy in the system to only predict spontaneity for that system. And we do that with Gibbs free energy. And the formula for Gibbs free energy is delta G, which is equal to delta H, which is enthalpy, minus T, temperature. This is given in Kelvin. This must be in Kelvin, times delta S, which is entropy. So be careful with matching units when we use this formula, because delta S is often given in joules, but delta H and delta G are often given in kilojoules. So you must convert. The definition of delta G is the amount of energy in a reaction that can be used for work. But in chemistry, it helps us to decide whether or not a reaction is thermodynamically favored or not. So if we have a positive delta G, or if delta G is greater than 0, and it's positive, then the reaction is not spontaneous. In other words, it requires energy for this reaction to go. It has to be added. If the delta G is equal to 0, then the reaction's at equilibrium. This is important to know. If the delta G is less than 0, or it's a negative number, then it's going to release energy, and the reaction is thermodynamically favored or spontaneous. So thinking about the equation above, we're going to look at the equations down here. They're all the same. Let's think about what combinations of the other variables, delta H, enthalpy, and delta S, which is entropy, would give us the negative value that we need to make a reaction thermodynamically favorable. So we want this number to be negative. So if we have a negative delta H, it should be right here, and we have a positive delta S, right here, our delta G would always be negative. Always, always. So we have an exothermic reaction and a negative delta H and a positive delta S, an increase in entropy or an increase in disorder would make this reaction always favorable. So it would always have a negative delta G at all temperatures. Doesn't matter what the temperature is. This combination is always thermodynamically favorable. So let's do this example right here where we have an endothermic reaction. This is endothermic. That's not going to help making delta G negative. It's going to work against us, so that's a big frowny face. And we have a positive delta S. Now remember, we want to increase entropy. And we have a positive number minus a positive number. This will be a negative. This will make this negative. So this is a good thing because we increase our disorder. Your entropy would have to be large right here in order for delta G to be negative. Okay, this needs to be large for delta G to be negative. So in this case, it will be a negative delta G at high temperatures and a positive delta G at low temperatures. So we would say that this is thermodynamically favorable at high temperatures. We would also say that this type of reaction is entropy driven because the entropy must be large in order for this reaction to happen. Now let's do another example. So we have now a negative delta H, which is exothermic, which we know a negative delta H will contribute to a negative delta G, so this is a good thing. And we have a negative delta S, so we're decreasing in our entropy. Now we know that decreasing in entropy is not a good thing. Decreasing in our entropy makes our reaction not thermodynamically favorable because we have a minus, a negative sign, which is essentially a positive sign. So a decrease in disorder, if you have a negative delta S, and that doesn't contribute to a negative delta G. So this number right here needs to be small. For delta G to be negative. All right, so the bigger this number is, better. So the bigger the better. These values drive the reaction. So in this case, right here, we'll have a negative delta G at low temperatures, and we have a positive delta G at high temperatures. So this type of reaction with a negative delta H and a negative delta S is thermodynamically favorable at low temperatures. And in this case, the larger the delta H, the more likely this reaction will become thermodynamically favorable. So this reaction would be enthalpy driven. Now let's go to this last example. We have a positive delta H, and we have a negative delta S. Again, this right here will change to a positive sign. So we have a positive sign and a positive sign. That will make delta G always positive. In this case scenario. So a positive delta G is an endothermic. I'm sorry, a positive delta H is endothermic. That's not a good thing. And we're decreasing our entropy, or we're decreasing our disorder. We know that that is not a good thing either. The delta H, a positive delta H and a negative delta S, that makes delta G always positive, no matter what the temperature is. And this reaction in the forward direction is never thermodynamically favorable. But the reverse reaction would be. For spontaneous reactions, a negative delta G, if the delta H is negative, the reaction is thermodynamically driven by enthalpy. We already spoke about that up above. If the delta S is positive, the reaction is thermodynamically driven by entropy. Other ways of finding Gibbs free energy include, if you are given standard values, your delta G is equal to the sum of the delta G of your products minus the sum of the delta G of your reactants. Looks a lot like the delta H and the delta S that we were talking about. All of those formulas are given on your reference sheet. So another formula that we're going to use is also given on your reference sheet is delta G is equal to the negative gas law constant times temperature times the natural log of K. Remember, K is the equilibrium constant. Okay, so use the balanced reaction below to answer the next few questions. So we have 2 sulfur dioxide gases plus 1 oxygen gas, and that's going to yield 2 sulfur trioxide gases. Use Gibbs energy equation to calculate the delta G for the reaction shown above. So our Gibbs free energy is delta G is equal to delta H minus T delta S. All right, we have delta H, we have delta S. It's not giving us temperature. Okay, so each of these say that they're at standard temperature. So we're going to assume that this is at 298. All right, on the AP problems, they will tell you that. So it should tell you that it's at 298, or it'll give you a different temperature. So this is what we're gonna do. We're gonna use 298. So delta G naught is going to equal a negative 196.6 kilojoules per mole reaction minus the temperature, which is 298 Kelvin, times the delta S, which is negative 189.6 joules per Kelvin mole reaction. Okay, so right here we've got kilojoules, right here we have joules. So we need to do a conversion on this. All right, I'm gonna change this into kilojoules because this is a big number right here, and we're gonna subtract this number times an even larger number if we change this to kilojoules. So let's just go ahead or if we change this to joules. So let's go ahead and change this to kilojoules. I'm just going to divide by 1,000, and that will be a negative 0.1896 kilojoules per mole reaction. And that's the number that I'm going to use here, a negative 0.1896 kilojoules per mole reaction, Kelvin. Okay, I've got a Kelvin in the numerator, a Kelvin in the denominator, so they go away. And my delta G naught will equal a negative 140 kilojoules per mole reaction. Is the reaction thermodynamically favored at 298? Why or why not? We have a negative delta G. Right here, negative delta G's indicate that there's a release of free energy, which means it will be thermodynamically favorable. Yes, negative delta G at this temperature. Therefore, spontaneous or thermodynamically favored. Which of the following statements is most likely to be true regarding the reaction above? The reaction is driven by delta H. So let's look. We have a negative delta H, and that causes our delta G to be negative. We have a negative delta S, a decrease in entropy, which causes delta G not to be favorable. Therefore, as long as this number right here is very small, it will be favored. Therefore, it is enthalpy driven. Let's do another example. Use the balanced reaction below to answer the next few questions. So we have 2 aluminum solids and 3 chlorine gases, and that yields 2 aluminum chlorides solid. Using the information in the table below, find the delta G of your reaction. So we're giving delta H formation, heat of formations, and we're given delta S's, or S's, entropy values, and we're asked to find delta G of reactions. So the formula that we're going to use is delta G will equal delta H minus T delta S. The reason we're going to choose this is because we have entropy values right here. We also have delta H values. So in order to find the delta H of the reaction, because this is of the reaction, these are heats of formation, we're going to have to use our delta H of our reaction formula, which is the sum of the standard heats of formation of the products minus the sum of the standard heats of formation of the reactants. Our S values, our delta S, will be the sum of the standard entropy values of our products minus the sum of the standard entropy values of our reactants. We're going to assume this is at 298. So our temperature will be 298 Kelvin. We should be able to figure our delta G out now. So let's calculate the delta H of our reaction first. So the sum of the heats of formation of our products, so we have 2 moles of AlCl3, and that has a negative 704 kilojoules per mole minus 2 moles of aluminum, which has a heat of formation of 0, plus 3 moles of chlorine, which has the standard heat of formation of 0. So the delta H of my reaction will simply be 2 times the negative 704 kilojoules, which is negative 1408 kilojoules. Now let's do our delta S. So our delta S will be 2 moles of aluminum chloride. Our entropy value for that is 111, and this is joules. Okay, so I'm going to put joules here, minus, because we're going to have to convert that, minus 2 times aluminum, the entropy value for aluminum, which is 28 joules, plus 3 times the entropy value for chlorine, which is 223 joules. So the delta S value is negative 503 joules per Kelvin mole. I didn't put the per Kelvin mole on here. I only put joules to remind me that it is in joules, but this is per Kelvin mole, or per mole Kelvin. All right, we need to convert this into kilojoules because I can't add a kilojoule and a joule together, which is the same thing as negative 0.503 joules per mole Kelvin. Now we're ready to calculate our delta G. So our delta G will equal our delta H, which is negative 1408 kilojoules, minus our temperature, which is 298 Kelvin, times our delta S, which is negative 0.503 kilojoules. This should say kilojoules. I don't know why I put joules. Per mole Kelvin. Our Kelvins cancel. And our delta G will equal negative 1,258 kilojoules per mole for the reaction that's written as is. Now it says to use the standard delta G values in the table below to find the delta G of the reaction. We just found the delta G of the reaction using enthalpy values, enthalpy of formation values, and entropy values. Now we need to use it using delta G values. So we know that delta G naught is equal to the sum of the delta G of our products minus the sum of the delta G of our reactants. So let's go ahead and do it, figure it out this way. So we have 2 moles of aluminum chloride, which in the delta G value for our aluminum chloride in the solid form is negative 629 kilojoules per mole. And I have 2 moles of it, minus 2 aluminums, which is 0. The delta G for the Gibbs free energy for aluminum is 0, plus 3 chlorines, and the delta G for chlorine is 0. So the delta G value for this would be a negative 1,258 kilojoules per mole reaction, as written. So what do you notice about the delta G values for the elements in their standard ambient temperature and pressure state? So we're talking about this right here. The delta G values are 0, just like the heats of formation. So these delta G values are 0. So how do the values in A and B compare? So negative 1258 kilojoules per mole and negative 1258 kilojoules per mole. They're the same. So you can calculate them either way. You can calculate them with entropy values and enthalpy values, or you can calculate it with delta G values. Is this reaction thermodynamically favorable at standard conditions? It has a negative delta G, so yes, it is thermodynamically favorable. Because delta G is negative. Let's look at this last example here. We have a hypothetical reaction that has the following thermodynamical data. We have the delta H of reaction is negative 548 kilojoules. Our delta S of reaction is a negative 38 joules per Kelvin. At what temperature does the reaction become spontaneous? Is it spontaneous above or below this temperature? A reaction is spontaneous with a negative delta G, and a reaction will switch when the delta G equals 0. It will switch from favorable to unfavorable or vice versa, depending on the temperature. So when our delta G is equal to 0, that's the temperature we're going to find out when it switches. So 0 is going to equal a negative 548 kilojoules minus some temperature, and this is what we're looking for, times a negative 0.038 kilojoules per Kelvin. I changed this right up here. I divided it by 1,000 because we need to change it from joules to kilojoules. That's where I got that. So this is the same thing as saying as a negative 548. I'm going to rearrange this. Kilojoules plus 0.038 kilojoules times temperature, and that's going to be in Kelvin. And if I bring this to the other side, it will be 0.038 kilojoules times temperature, which is going to be in Kelvin, is going to equal 548 kilojoules. If I divide both sides by 0.038 kilojoules, my temperature will end up being 14,400 Kelvin. That's a big temperature. All right, this is the temperature at which the reaction becomes spontaneous. Our enthalpy is a negative value, which will make delta G negative, but our delta S, or our entropy value, is negative, which, since it's subtracted, that makes this a positive value, this portion right here. So we need to make this portion as small as possible in order for delta G to be negative. In order to make this T delta S as small as possible, our temperature needs to be small. So temperatures less than 14,400 Kelvin would make this reaction thermodynamically favorable or spontaneous. And that's because delta G is negative at these temperatures. Okay guys, you're going to need to turn your notes over to the back page, and on that blank page write these 2 questions down, because we have some more notes we need to take. All right, the first one, we've learned that delta G is equal to delta H minus T delta S. What we haven't learned is delta G is also equal to negative RT natural log of K at equilibrium. That was touched on in the notes, but now we're going to talk about it. R here is the gas constant. There are several gas constants on your reference sheet. You need to use the one with joules in it because delta G is given in kilojoules. Temperature will always be in Kelvin. And this is natural log of K. This is your equilibrium constant. This formula right here is not on the reference sheet, but I did want to let you know another way to calculate delta G not at equilibrium. This is at equilibrium, and I know that because K is a constant at equilibrium. But if it's not at equilibrium, we're going to use Q instead of K. And the new delta G is simply delta G naught plus the ideal gas constant times T times the natural log of Q. So at equilibrium, delta G is equal to 0. So if these portions right here are going to be equal to 0, we can set this equation equal to this equation. All right, so delta H minus T delta S is going to equal a negative RT natural log of K. This is not given on your formula sheet, but both of these equations are. You need to know that equilibrium delta G is equal to 0, so you can set these 2 equal to each other if you need to calculate the equilibrium constant. Okay, I want to talk to you about some common mistakes that happen. This R, people not using the correct R. You must use the 8.314 R because that's in joules per mole Kelvin. The other R's are not in joules. The other common mistake is not converting the delta G to joules. If you can do one of 2 things. You can convert this to kilojoules, your 8.314. That's going to give a very, very small number. Or you can convert your delta G to joules, and that's usually what most people do. Those are the 2 common mistakes. Make sure you don't do those. Okay, so let's calculate the equilibrium constant, KEQ, at 25 degrees C for the reaction of N2O4 going to 2NO2 using the following data. So we're going to go with this reaction in the forward direction, okay, as written right here, in order to find the KEQ. Because if we go in the reverse direction, it will be different. So just as a reminder, in order to do the KEQ, or to calculate the KEQ here, I just wanted to show you a couple of things. Since these are both in gases, it will likely be the partial pressure of NO2 squared divided by the partial pressure of N2O4. We don't need this equation, but I wanted to remind you that that's what K is. It matters what direction we're going. All right, we're given delta G of formation values right here, okay, and we're asked to calculate K. So if we look on our reference sheets, if you can't remember how to do this during the AP exam or on the quiz, you're looking on your reference sheet for formulas that have K in them and formulas that have delta G. All right, we're going to use this formula right here that has delta G is going to equal a negative R times T times the natural log of K. Okay, we have G for each of these, the delta G's for each of these. So the delta G of my reaction is going to be the sum of the delta G formation of my products minus the delta G formation of my reactants. Now I have 2 moles of NO2, and NO2 is 51.31 kilojoules per mole. Times 51.31 kilojoules per mole minus, and my only reactant is 1 mole of N2O4, and that is 97.89 kilojoules per mole. My moles will cancel on each of these. And the delta G of my reaction will end up being 4.73 kilojoules. All right, I need to change this because my R right here is in joules, so I'm going to need to change that to joules. In order to change a kilojoule to a joule, I just need to multiply it by 1,000. So 4.73 times 1,000 will be 4,730 joules. And that's per mole reaction. All right, so I've got 4,730 joules per mole reaction is going to equal a negative R, that's a negative 8.314 joules per mole times Kelvin, times my temperature. It says it's 25 degrees C. This needs to be in Kelvin, so I'm going to change that to 298 Kelvin. I just add 273 to this, times the natural log of K. I'm going to rearrange this to look like the natural log of K, EQ, will equal 4,730 joules per mole reaction divided by a negative 8.314 joules per mole times Kelvin times 298 Kelvin. I should have canceled my units so I didn't have to rewrite these. A Kelvin in the denominator and a Kelvin in the numerator, since I'm dividing, will cancel. I have a joule in the numerator, a joule in the denominator. They cancel. I have mole reaction, and this is pretty much per mole reaction, so I can cancel those. So we have the natural log of KEQ, our equilibrium constant, will equal a negative 1.909, and there's a bunch of numbers after that. All right. Since this is the natural log, I'm going to do the opposite of that, and that would be e to the negative 1.909. So the KEQ will equal 0.148, and K's are unitless. Now let's do the second problem. Go ahead and pause the video and write this question down. It says a mixture contains nitrogen dioxide with a partial pressure of 0.1 atmospheres and N2O4 with a partial pressure of 0.2 atmospheres. Determine whether the gas mixture is at equilibrium. If it is not, in which direction will the reaction proceed? So we've already calculated our KEQ. up at the top, and we've determined that that is a 0.148. From this, we can tell that this is reactant favored because it's less than 1. I'm going to go ahead and write our KEQ expression from above, and that was the partial pressure of NO2 squared divided by the partial pressure of N2O4. All right, this is less than 1, which means we are reactant favored. All right, we need to determine if this is at equilibrium. And we know that if it's not at equilibrium, we do a Q expression instead. And the Q expression is the same expression as our equilibrium expression. So it'll be the partial pressure of nitrogen dioxide squared divided by the partial pressure of N2O4. So let's go ahead and figure out what Q is. The partial pressure of our NO2 is 0.1 atmospheres, and that's going to be squared, divided by the partial pressure of our N2O4, which is 0.20. We can do this mental math, so I'm going to go ahead and do that. A 0.1 times a 0.1 is a 0.010. Divided by 0.20. There are a couple of different ways you can do this, and I'll show you both ways. This is the same thing as saying 1/100th. All right, divided by 2/10. This is one way you can think of it. All right, this is the same thing as saying 1/100th times 10 halves. A 10 divided by 100, I can get rid of one of those zeros. It's the same thing as 1/10 times 1/2. This is the same thing as 1/20th. As far as decimals are concerned, this is the same thing as 0.05. Another way that you can look at this is 1/10 times 0.5, because we know a half is the same thing as 0.5. So 0.5 divided by 10 is the same thing as 0.05. We just moved the decimal place over one. So this is what our Q is. Our Q is equal to 0.05. Our K, EQ, is equal to 0.148. So our Q is less than our K, or 0.05 is less than 0.148. If that's the case, the reaction will proceed to make more product. And just as a reminder why, our Q is too small, which means we need to increase the numerator. In order to increase the numerator, we need to make more product.